everybody. Welcome to week 3 of Analog Lab. This week is going to be split into 2 parts. I'm going to go over a couple concepts at the beginning, and then I'm going to move on to a couple more laws and rules that we're going to go over, kind of more basic building blocks. The first thing I'm going to do is I'm going to switch over to my table camera, and I just want to talk briefly about wiring, because I had a couple people ask me about this. They were like, hey, I have all these really long wires, and I noticed that you also had smaller wires, and, how do I get small wires? And I sent you all a link to get a pack of these easy-to-use breadboard wires. And the reason I recommended this is because I think, doing breadboard circuits, these are really easy because they just kind of pop in, and they're kind of already ready to roll. However, in the early days of electronics, we did not have the luxury of using these kinds of wires. So I want to introduce you to the wire spool. In the old days of this class, we would recommend that you buy a spool of wire, as well as some wire cutters, and also some wire strippers. And for some of you, it might even be a good idea if you want to get yourself a spool of wire to cut and strip your own wire, and that way you can make wire to whatever length that you want. So first things first, before you just go out and get any spool of wire, I want to introduce you to the 2 main types of wire you're going to come across. This yellow spool on the right is stranded wire, and if I pull this up close to the camera, you can see that this is made up of a bunch of small strands of metal, right? So you might recognize this from your battery clips, right? It usually have to twist this together, and this is kind of annoying to have to put into a breadboard because it's a bunch of small strands, and sometimes they don't go in there. Sometimes you end up with strands that have not gone into the hole, and you might, potentially make a short circuit. So what is stranded wire good for? Stranded wire is used in a lot of soldering projects, and we're going to actually get into soldering today, and I'll kind of show you some good reasons to use stranded wire, because it's really bendy. You can put this inside of a box, you can bend it into any direction, and it's not going to break as easily. However, for this class, I might recommend to you to get solid core wire. You'll notice that this is just one single wire inside, and I can easily put it into the breadboard, right? And if I wanted to, I could say I only want a piece of wire to be this long, so I'll cut it to this length, and then I have to take this plastic sheath off. So there's all kinds of different wire strippers. These are a little bit fancy, but I can just pull this into this hole and clamp it down, and this will easily, maybe not on the first try here. Oh, you know what? I've got a little circuit board stuck to this. That will pull some sheathing off the end, so then you can use it in the breadboard. This is probably a little bit too much. I think these wire strippers are a little bit rusty. You probably only want maybe half as much of that, because you want to minimize the amount of exposed wire that will go into your breadboard. They make other kinds of wire strippers. This is a really fancy pair. Let me just kind of go over to some Google images here. If I look up some wire strippers. This is normally the pair that you would find at a hardware store or an electronics store. If I blow this up a little bit, it's got a bunch of different size holes here so that depending on the size of your wire, you can clamp this down and pull the sheathing off. If you are in New York and you go to Tinker Sphere, they might have wire strippers like this. A lot of hardware stores have them as well, or you could just order them online. Again, none of this is required for this class. I just kind of wanted to show you some other ways of doing things. So you don't have to go out and buy yourself any of this stuff. But if you get deeper into electronics, you're definitely going to have to cut and strip your own wire. And I'm going to be doing this today in class because I'm going to start talking about soldering. So I'm just going to keep my wire tools off to the side. Another thing that I want to talk about, because I had you get a bunch of different parts, which are these guys. These are from Adafruit, and these are connectors that can open and close. And I recommended you get these because this battery clip is probably really tough to plug into your breadboard. These are stranded wires at the end. And this one that I have, it's not as bad as others that I've seen, but sometimes the battery clip gets really difficult. So what you can do, and it's important that you only use one of these because, as you can see, there's metal stretching across this whole piece. So all three of these are connected together. So let's see. I can open up one, and let's just do this for the positive side of my battery. So I'll just poke that in there, and then I'll close this to clamp it down. And that's stuck in there. And then I'll take a red wire, and I only need to use 2 of these, but I'll just poke that in there and clamp that down. And so now, if I want to use this instead of the positive wire of my battery, I can do this, right? Like, this is going to stick into the breadboard a lot easier. Now, I can do the same thing with the black wire, but I have to use a different one of these because otherwise, if I connect the black where the red is, I'm going to have the black and the red connected together, and I'm going to make a short circuit. So I'm actually just going to quickly do this with the black wire, and I'm going to use this as an example from here on out because I actually would recommend doing this with your battery clip. Especially because the battery clip tends to be on the weaker side, and so this gives you a little bit more of a stronger connection by using these wires instead. And so, I'm just connecting them down here because that was closest to the camera, but you can see I've got one of these connectors for the negative side of my battery and one of these for the positive side of my battery. And if you're having issues with your battery, staying in the breadboard, I would really recommend using these 2 things to connect it. Cool. So I'm going to move this out of the way, and I want to start talking about soldering. So let's see if I can get this guy into the shot here. Okay. So this is going to be a little bit hard to see, but this is a soldering iron. So I can get some more focus. There we go. In this class, I would usually have you practice using this, but because we're not going into the lab this semester, we won't be able to actually practice soldering. However, it is a skill that is going to be useful, especially if you are going through analog circuits that you get yourselves, and if you play guitar and you want to repair your cables, if you are into running live sound with XLR cables and you want to fix those, it's not a bad tool to own. This model is a Weller. I don't know if you can see that there. It's about $25. These are exactly the same models that are at Steinhardt. So what I'm going to do is I'm just going to show you a couple soldering techniques, and I'll have you answer some questions, but soldering won't be a thing that we're doing in this class if you don't want to. However, when we are able to use the building again, there will be soldering irons available for you. And I would recommend just doing some practice if you can, because it is a really useful skill. So the first thing I'm going to do is I'm going to holster this. I have what's called a soldering station, which means I've got this little dial here and this on-off switch. So I'm going to flip this on. And I don't know if you can really tell, but this lit up with a little red light. And this dial goes from 1 to 5. And I'm going to put it between 4 and 5. There are more sophisticated soldering irons that use temperature. And just so you have a reference point, this is going to heat up to about 750 degrees Fahrenheit. So they get extremely hot. And so as this is heating up, I'm just going to kind of go over some safety precautions that we can go over so that you know how to use a soldering iron correctly. Let me see if I've got some solder in here as well. All right, I may have to hunt some solder down, but first things first. This iron is going to get extremely hot from here up to the tip, right? So we're going to always avoid touching the metal part. This under here is a sponge, and prior to this class, I wet this sponge with some water, and so this is always something you want to do. If you don't wet this sponge, it is not going to be as useful as a cleaning tool for your iron. But you'll notice I can just kind of like touch this to the wet sponge, and this will clean off any debris that's on the end of my soldering iron, right? So I don't have any solder here, so I'm going to take, oh, actually, I have a little tiny spool. I have some behind me, but let's just use this for now. So this is solder. This is a very bendable wire. You can see like that just broke off. So this really soft. In the old days, they used to make solder out of tin or lead, and lead, as you probably know, is super toxic. So it's important to have ventilation when you're soldering. However, lately they've developed new alloys using tin and some other materials. So there are solders that are not as toxic as the lead-based models from the past. I'm just going to kind of show you what happens. This guy should be heated up at this point, so let's just touch this to the iron. So you'll know your soldering iron's hot enough when the solder starts to melt, and you can probably see a little bit of smoke going on here, right? So solder melts really quickly, and now I have a lot on the tip of this iron. You'll see like a soldering iron is working really well when the tip is shiny and silver. So if you have buildup of anything on the tip of the soldering iron, you just kind of want to clean it off, you know, on a wet sponge, or they also make like a copper braid. But you'll know this is good to go when it's kind of shiny and silver at the end. Solder comes on a spool. I don't actually have a spool here, but we're going to use this little strand, and we're going to do some practice soldering. So I'm going to show you how to do two different soldering projects. The first one is going to be a potentiometer. Now, this is a potentiometer that is like a panel mount potentiometer. So you can see I've got a nut here. This is kind of like what you would find on a guitar pedal. So this is designed to have a hole. You push it through the hole. You screw this on from the top, and you can put a knob on here to turn it. So functionally, it's the same thing as the blue potentiometer that you're used to. It's just a little bit bigger. Now, I want to compare this to the potentiometers that you're getting for this class. You probably have them with these kind of pegs on the bottom. And this is really nice for a breadboard, right? Because I can just kind of shove that in there like that, and I can use it because it sticks right into the breadboard. However, you're also going to come across potentiometers like this. This has a series of solder lugs on the bottom. And so what I'm going to do is just kind of show you how to solder a wire onto something like this, right? And so what I'm going to do first is I'm going to take my solid core wire, because I want to use this with a breadboard. And I'm just going to snip off one wire. Now, there are 3 solder lugs here. It's the same process for each one, so I'm just going to demonstrate one. I would recommend, if you are soldering something like this, to use 3 different color wires, because you want to know which wire goes to which lug. It's also helpful to know which one's in the middle versus the 2 outer ones. So I would suggest, when you're soldering wires, if you have different colors, to use a different color for each lug. All right, so let me use my rusty pair of wire strippers, and we'll just strip off both ends. Okay. And I'm gonna get these little pieces of plastic. So I always like to have something nearby, like an ashtray or a little dish, so that I can put this stuff in and throw it away. Otherwise, you're gonna end up with little pieces of wire everywhere. So I just stripped off the plastic from the 2 ends of this. You can see the metal now. And again, if I was gonna put this inside of a guitar pedal, I might want to use the stranded wire because it bends easier, but because we're doing this for a breadboard, I'm going to use solid core wire. And what I'm going to do, and this is a technique that I use, but there's a lot of different techniques, I'm going to make a little hook on the end. I'm just going to bend the metal part into a hook, and I'm just going to hook it around one of these lugs. And I'm going to use my breadboard just to balance it. There are clamps and other things that I don't actually have in my apartment right now, but anything that will keep this thing in place is fine. So, what I'm going to do is I'm going to hold the soldering iron in my right hand because I am right-handed, and I'm going to hold the solder in my left hand. Now, one thing that I want just to point out is it's not like we're not painting on the solder. This is going to transfer heat to the part that we are soldering. If I lift this up, this is going to start getting cold. So what I want to do first is I want to touch this solder joint at the point where the wire touches the potentiometer. And I'm just going to leave it here for about 10 seconds. And as I have this here, then I'm going to add the solder and bring it in. And I'm going to leave the iron in place. I'm not going to touch the iron. I'm just going to dab the solder on there. And what should happen is the solder should fill this hole entirely. And after that happens, I'm going to put my solder back in the holster. I'm never going to place the solder down on the table, the soldering iron, sorry, because this gets really hot, right? And I could burn my table, I could burn anything else. The holster is always where this thing goes. In about 10 seconds, this solder joint is totally rigid, right? And so this is now totally attached to this potentiometer. I could bend this a lot, but like a paper clip, it might break because it's solid core. One of the drawbacks of solid core wire is it breaks easily, but if I wanted to use this in my breadboard, now I could just plug it in, and I can attach other parts to my breadboard. Right? So a lot of things get soldered like this. Switches, any sort of panel mount things, if you're familiar with guitar pedals or synthesizers, you know, a lot of things are not attached directly to the circuit board. So you will attach wires to them, and those wires will be attached. And then you can have this really as long as you want. You know, after a long, long length, you're going to have some voltage problems, but generally speaking, if you're making a project and you want it to look, you know, semi-professional, you might want to solder some things like this. So this is how you solder a component. I'm going to also show you how to solder a circuit board. And so I have this little project here. This is a little amplifier that I got from Adafruit. And it doesn't really matter, but I'm just going to like dump this out and kind of show you how I would solder something like this. And so what's interesting about this is that this is an amplifier that's meant to use the breadboard. And so, you know, they have these header pins, which can easily stick into the breadboard like that. And what I'm going to do is I'm just going to grab enough so that I can pop them in here, and I'm going to break off the remaining ones. They usually give you more than you need. And I'm going to stick the short side into my circuit board so that it's kind of sticking in the bottom. Now, for a project like this, what I kind of like to do is pop it into a breadboard, because that way, like, this isn't attached yet, but at least I can solder it easily because the breadboard's kind of holding it in place. So, let me zoom in a little bit. I want to see if I can get a closer look at this. So now this is going to be a little bit harder, but it's pretty much the same technique. I'm going to heat up the place where the solder touches the pin, and you'll notice this is kind of leaning a little bit because there's nothing under this side. So I might just like stick something under here just to kind of hold it up a little bit. So now I'm just going to start with each hole. I'm going to touch the iron to the place where the hole and the pin make contact, and I'm just going to add a little bit of solder. And once it makes kind of like a teardrop shape where I can't tell where the pin and the hole are, then I'm good. And I'm just going to move down the line and touch each pin. And you'll see it takes only maybe a second or two to fill that hole. So let me zoom in a little bit more here so you can kind of see what's going on. So you'll notice, right, each of these solder joints is now individual. There is space between them, and that's really important because these are all separate connections. And I want to make sure that I don't have what's called a solder bridge, which is basically solder that is connecting one pin to another. Now, just for the sake of showing you what that looks like, I'm going to make a solder bridge. I'm just going to like add a little too much solder to one of these and just kind of connect them together. Right, so now I think you can see those first two pins are bridged. I've added too much solder, and now they're connected. And what's worse, this is power and ground. So I've created a short circuit on this board. But what I can do, let me see if I can do it vertically. I'm just going to heat that up and kind of like push the solder. And you can see like it kind of wants to not be in between, right? I can kind of drag this so that the solder isn't on both. And then I'll just wipe off the excess on my wet sponge that I already have. And I can keep doing this until I am certain that I don't have a solder bridge. Right? So once the solder dries, you can always reflow it, remelt it, and kind of like drag it around with the soldering iron. They also make something called a de-soldering pump, which is a suction that you could use to remove solder. There's a lot of ways to do de-soldering, but it's a lot more difficult and messy than actually soldering. So yeah, that is pretty much all there is to soldering. You're either going to be soldering parts to a circuit board like this, in which case, like, it's pretty easy. Like, now I have these little screw terminals. If I wanted to pop these in, right, I would just need to flip this over and solder on the underside. And now my pins are all connected, which is really nice. And I would just need to solder there, and I could just pop that down on the table and do those. I'm not going to do this whole board because I want to go over some other stuff. But pretty much you're going to be doing circuit boards, or you're going to be doing components, and the kind of method is the same for both. You're going to leave the iron on there until it heats up, and then add some solder. There is a lot of different ways to solder. There's something called surface mount soldering, which is done with a hot plate and tweezers. You can probably imagine, like, the components in your cell phone are too small to do by hand. There's a lot of machinery that does soldering. Go on YouTube and watch some videos of soldering. There's tons of it out there. It's like this weird ASMR thing where people are just soldering for hours on YouTube. Watch reflow soldering, watch surface mount soldering, just check it out. It's not a difficult technique to master, but I would encourage you to at least give it a shot if you have access to a soldering iron. You may not have access until the spring because these are at NYU, but maybe you want to grab yourself a little soldering station and practice in the meantime, especially if you plan to get any sort of like guitar pedal kits or synth kits or anything. Usually you have to solder them together. One very important thing, I'm done using this, so I'm gonna turn it off. This is super, super important. You never want to leave this thing on because it's a fire hazard, right? Like, something could accidentally fall over and touch this iron, and you know, who knows? So no matter what, always, always, always remember to shut this off at the end. If you have any questions about soldering, please contact me. I've been through many brands of soldering irons. I can recommend affordable models. I can recommend really fancy models if you want. It is something that I have used almost on a daily basis working on electronics, and it is certainly a skill that you should master, even though we won't really get to do it this semester. Okay, so let's kind of go back, and basically the first part of this lab is I want you to answer two questions. You've walked over to a soldering iron. You are standing in front of the iron. It is switched off. Tell me everything you do up until the moment at which you touch your iron to the component you're about to solder. Some good things to include are around where do you set the temperature on the irons we have in the classroom, which, remember, are identical to this one. How do you clean and prepare the tip of the soldering iron? And anything else you can think of from what I just showed you. Second part is you've just finished soldering your last joint. What do you do before you step away from the soldering iron? Some good things to include are what extremely important safety precaution do you take? What do you do to be kind and helpful for the next person, and anything else you can think of. So, you know, I thought about not including soldering in this class because of, you know, us not having access to the irons in the lab, but it is such an integral part of analog circuits, I think, you know, it wouldn't be fair to not include it. So there is no required soldering this semester, but if you do want to do it on your own, come and talk to me. I'd be happy to make recommendations. for ions. Okay, so let's move on to the math part of today. I'm just going to move some of this stuff out of my way. We are going to measure current this week, and we're going to learn about Ohm's law. So, I'm going to switch back to my table cam, and I'm going to look at my soldering iron, or my multimeter. So, I want to show you something on this multimeter and the one that you have at home. This has two different holes here for the red plug to go into. And I'm just going to pull this out for a second. And this says fused 500 mA max. Well, this is what we're talking about today. Milliamps. Amps are a unit of current, and this port can handle measurements up to 500 milliamps. Milliamps are 1/100th, so this is actually 0.5 amps. After that, I have to plug it in over here. And this says 10 amps max. So, what you need to know about amps, you measure it in much the same way. Here's the A over here. And you'll see it has 20 milliamps, 200 milliamps, 10 amps. So if I move over here, this is going to be my other port. Now, how big is an amp? 1 amp is actually quite a bit of current. I doubt we will ever need to move this over to this port for this class, because 500 milliamps is a pretty good amount of current for audio circuits, and I really don't think we'll ever need to use this. So I want you to know why this exists, but that we're probably only going to use this. There are fancy multimeters at the university that all the current measurements have to go into the other plug. So you pretty much measure voltage and resistance and everything here, and then when you're measuring current, you switch it. But on these cheaper models, we can probably use the same plug for everything. So, that said, let's talk a little bit about what current is. And so I'm going to go, let's talk about Ohm's law a little bit. So you might remember this from high school physics if you had an electronics course. V equals IR. Actually, let's use this for a minute. So this is Ohm's law. This is one of the basic building blocks of electricity. Voltage, resistance. Now we're going to talk about I, which is our current. And this is going to be measured in amps or amperes. So this is the relationship that we can use to calculate how much voltage is being consumed, how much current is being drawn, how much resistance a certain component needs. Something to keep in mind. In a circuit, generally speaking, you have a set amount of volts. You have a set amount of resistance. And the current is always determined by these two things. So a piece of electronics will draw current. And the more current it draws, the hotter the circuit is going to get. I like to think about this as like there's like a water analogy where your voltage is kind of like your water tank, and the resistor is kind of like the size of your pipes. Well, the speed of the water at which it flows through the pipes is your current, right? Another thing that we can use to look at is a power supply, right? So here's a power supply, and I can look at the rating on here, and this says output 5 volts 2.0A, right? Which means if I plug something into this, it's going to be a 5-volt power supply, right? That will never change. But the maximum amount of current this will provide is 2 amps, which is actually a lot of current for a little supply like this. But that means that if I have a device that's 5 volts and it only draws like 500 milliamps, that's perfectly fine. As long as I don't exceed 2 amps, this thing will work, right? So whenever you look at an adapter like this, the amp rating is always going to be the max amount of current that this can provide, whereas the voltage is always going to be 5 volts no matter what. Something else that we might want to talk about here is the input, right? Notice this says 100 to 240 volts, which this happens because in different countries you have different voltage coming out of the wall. So in the US, we have 120, so that's fine. But if I took this to Europe, I could also plug it in because Europe is 240, and so this can handle 240 volts. So if you're ever curious, if you're traveling, whether or not your adapters can handle different voltages, you can just look at the input and see. So if you ever want to use a power supply like this, you can always look at the ratings here. We are going to use batteries, and batteries, you can draw pretty much as much current as you want from batteries. They'll just die faster. So batteries are sometimes give you an amp hour rating, which these kind of cheap 9 volts don't, but if you get like a lithium battery, it might say like 1 amp hour, which means it will provide 1 amp for 1 hour before it dies. Or it'll provide 2 amps for a half an hour, right? Or it'll provide half an amp for 2 hours, right? Does that make sense? You're like just adjusting the ratio depending on how much power you're using. Okay, that was a little bit of a tangent. So, voltage, current, and resistance are always related. If you don't have one, but you have the other two, you can always calculate what it can be. Now, typically, you're not going to really have amps unless you want to say, like, oh, what's like the maximum amount of resistance I can hook up, in which case you can calculate for that. The other really important equation here is this one. And this is the power equation. This is like another version of Ohm's law. Power is measured in watts, and this is your current in amps and your voltage in volts. So you might have a 60-watt light bulb, right? So let's just do this really quick. If I have a 60-watt light bulb, and I know that my voltage in my house is 120 volts, right? Then I could divide both sides by 120. And I can say that 60 divided by 120, 1/2 amps. So my light bulb, if it's a 60-watt light bulb, is consuming about a 1/2 amp of current, right? And so you can calculate this for almost any device. If you want to go around your house and do this, you can. This is why you might trip circuit breakers in your house, because typically in an apartment, you've got a 15 or a 20 amp circuit breaker. So if you turn on the microwave, which is like maybe 1,000 watts, and then you turn on an air conditioner, or you turn on another thing, you might max out the amount of amps that you have on your circuit breaker, which causes the breaker to trip. So sometimes some of you might have realized this happens, like if you turn on too many things and something trips, it's because you've exceeded the number of amps that can be supplied to power things. So we're not going to get into that too much, but just to know how current works. Current is not usually a definitive thing. It is something that gets determined by the circuit when you hook something up and you start drawing power. So what we're going to do is we're going to do this quick exercise. So Here are the two equations that I just wrote down: V equals IR and P equals VI. I wrote it IV, it doesn't matter. So what we're going to do is we're going to solve a problem. All of the resistors in our kit are rated to be a 1/4 watt, meaning they can withstand up to 1/4 watt of power before they overheat and destroy themselves. You might recall from last week, I kept telling you to use really big resistors, 10K or above. Why? Well, if you just picked any resistor, you might pick one that is too small for a 9-volt battery, and if you hook it up, then it will get very hot and it will, not work anymore. So what we're going to do today is I want you to determine the smallest resistor that you have on hand that can safely be connected directly to your battery. I want you to use the measured voltage of the battery. Since you may remember, a battery can be more than 9 volts. Show your work and then test with the multimeter. So, I'm going to not solve this for you, but I'm going to write down our givens and then I will let you solve. So, first things first, I'm going to measure my battery because it may have changed from last week. .9 and 9.0. Lucky me. Hit it right on the nose. So, my voltage equals 9.0, and my current equals 1/4 of a watt. Or sorry, my power equals 1/4 of a watt. I'm going to solve for R. And I want to use these two equations, right? So, I know 0.25 watts is the max. I know I have a 9-volt battery, but you maybe have something different. Maybe you have 9.2 or 9.3. Make sure you write down exactly what that is. And then, using these two equations, I would like you to solve for R. Okay? So, I'm going to let you pause the video if you like and do that. Okay, now, you've probably solved and have this really crazy number, and chances are, if you look in your resistor kit, you do not have a resistor that is that value, because your resistors are 220 or 330. So what you're going to do is you're going to choose the next highest resistor, right? Because if you've solved for this number, and this is the lowest possible resistor you can use, well, you're going to have to round it up to find out what your actual resistor is that you're going to use in this experiment. So, I want you to do that. I want you to round that number to the nearest resistor in your kit, round it up. Otherwise, you're going to go below your minimum value. And then we're going to measure the current. Okay, so how do we do this? First of all, I'm going to show you this, this schematic. Now, when we measure current using a multimeter, it's a little bit different than measuring voltage. Because when we measure voltage, as you may recall, and I'm just going to use a random resistor as an example. When we were measuring voltage, right, we took our probes and we put them on either side of the resistor, right? We effectively created a parallel circuit with our multimeter, because remember, it's connected to the same two places to measure voltage and to measure resistance and all that sort of thing. Well, when we do current, it's a little bit different. We actually have to measure in series, right? So what I'm going to do here is I have my battery, I'm going to plug it in. And I have my resistor. This is not the resistor that I solved for, so I'm not going to give you the answer. But what I'm going to do is I'm just going to connect it to power and ground using 2 wires, right? So I'm going to connect this side to power. And I'm going to connect this other side to ground. And nothing is going to happen, right? Because it's just a resistor, right? There's not anything to see here. I could measure the voltage across, and I should see my 9 volts, right, drop across here. A little bit less. Now, if I want to measure current, I'm going to have to break this circuit because I need my multimeter to be in series with this resistor. So what I'm going to do is I'm going to take out the positive rail and just kind of stick this wire straight up in the air, right? Now, what's going on here is this is a broken circuit, right? I won't get any voltage now because I've disconnected one side of my circuit. But I'm going to turn this to, let's go to 200 milliamps and we'll see what happens. Now, what I'm going to do is I'm going to take one probe and put it here, and take the other probe and put it here. And you'll notice for this random resistor that I chose, I'm measuring about 9 milliamps, right? And I know it's milliamps because I'm turned to the milliamp setting, even though it says 9.0. This is a little bit confusing, but generally speaking in this class, we are dealing with milliamps and not amps. So I'm not going to tell you what this resistor is, but if I know that my voltage is 9.0 volts and my amps are 9.0 milliamps, which equals 0.009 amps, I could use this equation and I could say 9.0 divided by 0.009 to solve for my resistance, and I will get 1,000 ohms. So this is a 1K resistor, right? So what I want you to do is measure that resistor that you solved for in the previous problem, and I want you to measure this. And then I want you to just see if the amps that you're measuring here match the amps that you calculated here. Now they should be slightly off, because remember, we rounded that resistor, but you should get a value pretty close to what you solved for here. Okay? So, basically, you're going to determine the smallest resistor that you have that can safely be connected from power to ground. You're going to use the measured voltage of your battery, show your work, and then I want you to measure it with a multimeter using this in-series configuration and just compare the amps that you measured to the amps that you calculated. Okay? And clearly show me the calculated and the measured values. Okay? Last part of the lab. Last week we did Kirchhoff's voltage law. We said that for any given circuit, for any given series circuit, all of the voltage drops in series will add up to the total voltage of the circuit. Okay? Kirchhoff has another law. It's called Kirchhoff's current law. Kirchhoff's voltage law applies to series circuits. Kirchhoff's current law applies to parallel circuits. Basically, the current law states the sum of the currents flowing into a point in the circuit are equal to the sum of the currents flowing out. So I want to show you this circuit. Basically, what we have here is 4 resistors in parallel. And so we know, because these are all in parallel, that they're all going to have a voltage drop that is equal, right? When we measured parallel resistors with the multimeter, we're going to measure the same voltage across all of them, because they're connected together, right? So you would have, if I have a 9-volt battery, I would measure 9 volts across each resistor. However, current does not function that way. Current is going to split, and current is going to flow through each branch of this circuit differently. And the sum of the currents in each of these branches will add up to the current that is coming in. So in this circuit, I1 is equal to I2 plus I3 plus I4 plus I5, right? The current that is in each of these separate branches. And that is also equal to I6, okay? So you have current going in, I1. It splits up into 4 different currents, and then it adds back together in I6. So what's going on here? Like, let's think about this in the water analogy. You have water coming into a junction point, and then you have these different sized resistors, right? I have a 1K, I have 2 1Ks, I have a 2.2K, and a 3.3K. So take out those 4 resistors, and I want you to put them in parallel. Basically, depending on the size of the resistor, you're going to have more or less current. So if I think about this, right, R4 is 3.3K. That is the largest amount of resistance. Well, you could think about this, if you have the largest amount of resistance, you probably have the least amount of current. Whereas the 2 1K resistors should allow more current to travel through. And they should probably be equal, right? Because I have the same amount of resistance in both of those branches, so I should measure the same amount of current. And my 2.2 branch in R3 is going to be somewhere in between. So, what I would like you to do first is I would like you to calculate what these currents should be, okay? And so, let's see. I might be running out of space here. Basically, I have my 4 resistors. I have R1 equals 1. I'm going to write 1,000 because I want to make sure I don't forget to do that. R2 is also 1,000. R3 is 2.2K, so it's actually 2,200. And R4 is 3.3K, or 3,300. I'm also going to take my measured battery voltage, which for me is 9.0 volts, but for you, it's probably a little bit different. And make sure you use this, because when we measure this, we want to make sure we're using an accurate voltage reading here. So I'm going to use V equals IR to solve for the current through each of these branches, right? So basically, looking at this, right? Solving for I2, I3, I4, and I5, that's easy. That's just going to be my voltage divided by my resistance. However, for I1 and I6, I'm going to need to solve for the equivalent resistance here, right? So remember last week when we figured out how to calculate the resistance of 4 resistors in parallel? We're going to do that again. We're going to do our 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. I want to know if this whole mess was just one resistor, what does that resistance equal? And then, once I have that, I can solve for I1 and I6. So, before you do anything with the breadboard, I want you to run through these calculations. I want you to solve for I1 through I6. I1 and I6 are going to be the same calculations, so that is totally fine. So, do that now. once you are done, we're going to build it. Now, for this exercise, I recommend using 2 wires, like I did earlier, to attach your resistor networks to power and ground, right? So, I'm not going to actually use the same resistors because I want you to measure them, but I'm going to use 4 resistors to demonstrate how you can do this. And what I'm going to do is I'm going to make sure that I use all of the holes in these 2 rows. Because there's only 5 holes, and one of them is taken up by my power and ground wires. The other 4 are going to be these 4 resistors. All right, 4th one in here. These are all pretty big, so I'm going to get some different current measurements. But basically, this is my circuit, right? I've got these 4 resistors all in parallel, and I've got power going into the top and ground going into the bottom, right? So I've got my voltage going into the top and into the bottom. Once you have solved for what the currents should be, I would like you to measure what the currents should be. So, let's take a look at this in the schematic again, right? Everywhere that I see this current A circle, I need to break the circuit and put my multimeter here, okay? I'm going to skip over I1 and I6 for a minute, and I'm going to move to these branches. So, basically, for each branch, what I need to do here is remove one end of my resistor, and I'm going to measure from basically where that used to be plugged into to where it is now, right? And I'm going to record that measurement. And then, to do the next one, I need to put this back, right? Because this resistor has to be back before I can measure the next one. And then I'm going to do the same thing. I'm going to put one probe where this used to be plugged in, and then I'm going to put the other one on this part that's unplugged. And I'm going to record the measurement, right? So I'm going to do that for those 4 resistors, and that should give me the 4 current measurements that I need, right? Now, let's look at I1 and I6. Basically, I1 wants me to break the connection between the plus side of the battery and my entire network, and I6 wants me to break the connection between the negative side of the battery and my entire network, which is why this configuration of resistors works really well. Because what I can do is just unplug my power from here, just like I did with 1 resistor, but I'm doing it with 4. I'm going to measure from here to where my resistors are and record that. And then I'm going to put this back. And I'll do the same thing on the other side. And I'll measure from this to there, okay? So basically, when I'm measuring current, I am inserting the multimeter in series with the circuit, right? I'm breaking the circuit and I'm measuring where it should be. Now, you should get measurements of current that are pretty close to what you calculated, especially if you used the right battery voltage. If you didn't, check your measurements, check your circuit, make sure that everything is kind of not touching, especially here, you know. It's okay if this side all touches because they're connected together anyway, but always be careful about metal that's touching because that can cause incorrect measurements or a short circuit. And that's it for today. You know, the current is going to be something we talk about a lot. We are doing a lot of current and voltage and resistance measurements throughout the semester. And so knowing about the relationship between these things is really important. If you have any troubleshooting, jot that down. And yeah, otherwise, that's it for today. I will see you all in office hours. Have a good night.